Hello and welcome to my introduction to the CNC milling machine at Xerocraft. I'm going to be going over some of the basics of setting up the machine with a bit of an expectation that you've had some exposure to CNC machines, probably the CNC router, in the past. Now the first step, of course, is to design the cam or toolpaths that the machine will be doing. And to do that, we're going to get started in Fusion 360. Now, Fusion 360 is a fantastic software that merges 3D modeling with CAM or toolpath generation, and it's a very popular choice in the hobbyist and maker community because it is free for non-commercial use. I'm not going to go into all the nooks and crannies of what Fusion 360 can do. That is far beyond the purview here, but I'll show you some very basic stuff. If you're unfamiliar with these sorts of engineering softwares, it essentially boils down to drawing 2D sketches and then modifying them, pulling, pushing, rotating them to form 3D shapes. And so I'm going to get started by showing you how to make a simple tightening fixture that looks like this. This particular part is very handy when used with the ER32 collets that I'll be showing you in a little bit. It helps to tighten the tools in the collets. So we're going to get started, as we always do, by creating a new sketch over here. The first part of drawing a 2D sketch is to define which plane the sketch is going to be placed on. And so I'm going to start here by choosing this plane. It doesn't really matter a whole bunch when we're first getting started, but what I'm going to do here is I'm now going to use these 2D drawing elements to create my shape. So I'm going to first start with the circle, and so I can click once to set the center of that circle, and again to set the diameter, or I can type in the numbers. In this case, I know that that's going to be a 40 millimeter outside diameter, so I can just type 40 mm, and that will set it to be that number. Right now we happen to be in inches. We can change that up here if we want to. The next step is to flatten two opposing sides. I'm going to do that by creating a rectangle. There's a few different ways I can define a rectangle, and for ease here I'm going to set this to be a center rectangle. So again, I'm going to click to set the center, and then I can either draw it out here, or I can simply type this here. Could be something like 2 inches, and then I'm just going to hit tab and switch over, and I know that I want 36 millimeters between the flats, so I'm just going to type 36 millimeters there and hit enter. And so now I have my parent circle and the flats drawn here, and I'm simply going to use the trim command to delete away all the line segments that I do not want. So I'm going to delete all of these little extra sketches over here, that and that, and so I'm left with my parent circle with the ends chopped off. And then last but not least, I'm going to want to draw a box around this for the extent of this part. So I'm just going to simply draw another rectangle, another center rectangle, which I will set up here. And this is somewhat arbitrary, but I'm going to go ahead and make this something like, say, 3 inches by 2.5 inches, just like that. And now I'm complete with my part, and so I'm going to say finish sketch. Now I have my two-dimensional sketch, and I'll do the most common thing to do, which is an extrude. So when I click on this surface here, now that I'm in the extrude command, what I'll do is I can now take that 2D sketch and extrude it into the third dimension. In this particular case, I'm going to use some material that's 3/8 of an inch, or 0.375 inches in thickness. And so I can now say, OK. And here is my finished design, exactly as I want it to be. And so now my 3D modeling is over, and it's time to switch over to doing the machining part. So that is as simple as going up here and switching from the design view to the manufacturing tab. And so now we have a whole bunch of new tools up here at the top that will help us set up the machining. And the first thing that we're going to have to do is to create what Fusion calls a setup, which is essentially describing what the material is and how the part is being held in to our machine. So I'm just going to go ahead and click Setup here. And so the first thing that we're going to see here is some very basic stuff about setting up the work coordinate system. And in this particular case, what we can see here is we've got X, Y, and Z defined based on how we had it set up in the design side, as well as with the 0 point being where it was before, the origin, which in this case happens to be right dead center of the part. Now there's a couple of things I'm going to want to change about this. First off, I'm going to want to use the corner to be the XY 0 point, because it's going to be a lot easier to accurately find the edge of my part rather than the center. The other thing I'm going to want to do is I'm going to want to define the X, Y, and Z coordinates a little differently because of how the machine actually works. And so to basically what's going to happen is in real life the x-axis is going to be left and right as we're looking at the machine. The y-axis is going to be away from us and towards us, and then the z is going to be up and down. So what I can do is I can say for the work coordinate system, rather than having the orientation as it's defined in the model, I can just select my x and y axes. So I can force the x-axis to be, say, this vertex of that part, and then the y-axis I can force to be this way, which is going to make my life a lot easier. Now it looks like it's moved my origin point, so I'm just going to go back to selecting the stock, and I'm going to go here. And so now I've got it set up as I wanted. My x-axis is going to be running this way along the part, my y-axis going this way, and then z is going to be vertical straight up this way. Now, the next thing I'm going to do is I'm going to work with the stock itself. Now, it's very important that the software know exactly what piece of material, what size material I'm going to be using, because this program is going to be making assumptions about where it can be moving quickly, safely, and the last thing I want to do is have it think that there's air in a place where there's actually metal. And so it's very important that we give it those precise dimensions. Now you can see it's defaulted to a relative size box, where it's just assumed that the material I'm starting with is just 1 millimeter bigger in all the axes than my finished part, which may not be true. And so in my particular case, what I'm going to do here is I'm actually going to go ahead and use a fixed size box, which I can define based on measuring the exact piece that I'm going to use, and that is simply going to be something in the neighborhood of, say, 4 inches wide by a depth of 2.5 inches, and there is my material all set up and ready to go. Now, because we live in America and all of our tools and setups are going to be in inches, I'm going to switch the dimensions over to inches right here. And now we're going to set up the toolpath to create this pocket here in the middle of our piece. And because this is a two-dimensional type shape, we're going to use the 2D operations and do a 2D pocket. Now, no matter which of these strategies we use, the first thing that we're going to want to do is tell it what tool we're using. So I'm going to click Select, and that's going to pull up the tool library. And you can of course create your own tools, but the ones built in are a pretty good place to start. So I'm just going to start with a sample tool in the inch dimensions. I'm going to filter to milling tools by flat end mills, and here is the 5/16 diameter tool that I'm going to be using for this part. And then down here I can select what material I'm using, in this case aluminum, and what sort of strategy I'm going to be taking, and this is going to be a roughing strategy. And so that has propagated all of these parameters about the tool, both its geometry and how it wants to be run. So I'm going to select this here, and that's propagated all of these feeds and speeds information into our spreadsheet. The problem is that the machine that we have is not got the fastest spindle in the world. And so while 12,000 may be doable, in our particular case the machine can't go any faster than about 5,000. So I'm going to have to change these numbers here to about 5,000 RPM. And what we'll see is that this computed surface speed, aka the speed at the outer edge of the tool, has come down quite a bit, from almost 1,000 feet per minute to 400 feet per minute. This is one of the critical numbers that you'll want to look up if you have to come up with these speeds and feeds entirely on your own. Now the next thing that I'm going to want to do is, because I reduced the RPM of the spindle, I'm also going to have to reduce the feed-in or the feed rate in order to maintain a safe feed per tooth. This number is again something that you're going to want to look up from the manufacturer of the tool. Generally speaking, a larger tool can take a bigger bite, and softer materials can be chewed more aggressively. In our particular case, I'm going to go with a pretty conservative 1/1000th of an inch, and that's going to set my feed rate to 15 inches per minute. I could probably take double or even triple that feed per tooth, but I'm going to be conservative here and just go at a relatively slow speed, just so I don't embarrass myself breaking something. So I'm just going to change all of these other numbers to 15 inches a minute, and that's all my feeds and speeds set up. Now the next thing I'm going to want to do is I'm going to want to choose which geometries to focus on. So I'm just going to select the pocket here to tell it that this is where I want to be doing my machining. I can also set up things like heights, where it should clear to, how far it should go, etc. And I can also set up my passes. This is really handy. This is going to help me out with stuff like how close I should get to hitting the exact shape versus simplifying the geometry by not producing 10,000 points along a curve. I can also do stuff like here, because this 2D pocket is considered a roughing strategy by default, it will leave a little bit of material for us to clean up at the end. Now, I don't actually care. I'm not going to bother with that. So what I'm actually going to do here is not just set this to 0, but because I want to make sure my piece fits, I'm going to choose to have actually a negative stock to leave here. So I'm going to intentionally cut 5/1000ths of an inch past where my line actually is, just to make sure that things fit nice and smooth into there without having too much problems. Now, I strongly encourage you, when you're doing this on your own, to be pretty confident in most, if not all, of the parameters here. Fusion 360 has some great tooltip advice for you. So if you hover over one of these options, it will pull up a little preview explanation of what this means. It's very important that you understand what it's trying to do, because there are all sorts of gotchas here that you can get yourself in trouble for. So just be a little careful, especially when you're running your first operations. But I'm happy here, so I can simply go ahead and hit OK. And so it's now going to calculate where I should go. And you can see here, here's the tool. what it's going to do is it's going to spiral down nice and slow to form a starting spot for this pocket. And then from there, once it's gotten all the way to the bottom, it's going to make these concentric circle-like shapes until it gets out to the finished dimension, and that is my part. Now, I could also have this set up to cut the outer edge here, but I'm not going to bother with that. That's just as easily done with a saw or whatever else. I haven't yet decided how I'm going to hold this, so I'm just going to make this part and attach it to some sort of bracket or, piece of angle iron or something later on down the line. But this is everything that we need to do here, and so we are done creating toolpaths. Now, one thing that you may want to do is to simulate the toolpath. So if I click up here, I can watch a little video of what the machine is going to do as it's making my part. And so we can watch it as it spirals in. Some nifty stuff, in the tool setup, it's actually got the length of the tool and the geometry of the holder and everything, so we can be really extra careful that we don't crash something into something else. But we'll watch it here as it goes and makes the part, and that all looks like it should come out okay. And now the last thing to do is to export this G-code. And so what we're going to do here is, this is called post-processing, where the manner in which it exports the G-code is going to differ slightly depending on the machine and the software that's running the machine. And so while G-code is pretty universal, it's not totally universal, and so we have to be a little careful here. The first thing that we're going to want to do is choose the post-processor that's appropriate for us. There is a whole bunch of them in here, and while I'm sure one of these is probably good enough, what we really want to do is go and get one of the not pre-installed ones. And we're going to click here to search in their web system to find the one for Mach 4. So I'm going to come here and say Mach for mil, and I'm going to download that. And so what that's going to let me do is I can go back into Fusion 360, and now that I've downloaded that Mach 4 post-processor, I'm just going to change the configuration folder from its default to my downloads folder. And lo and behold, the only thing left in my options is the Mach for mil. And so now we're pretty much ready to go. The one last thing to do here, which is pretty important, is on our machine, this safe retract here should not be G28. This is a command that will absolutely crash the machine in its current status. So rather than retracting using this fancy G-code operation, I'm simply going to say, hey, when we're done, let's just go up to the clearance height, which I think by default is like a half an inch above the part. And so that's pretty much it. All I have to do is say post, and this will now save that G-code to a file that I can run. So now we'll switch over to the physical part of running the CNC machine, and that's going to start very simply by turning the machine on. Now on the left side, what you'll see is a standard PC power plug along with the main power switch that you'll want to switch on. And then on the right side, you're going to see a whole bunch of computer ports along with 2 buttons, and when the main power is on, if you press the little green button, that will boot up the PC that runs the machine. Now to hold the part, I'm going to use what's probably the most typical strategy, which is a vise and a set of parallels, which is going to hold the part up out of the vise. You really don't need very much contact with the jaws, but it's very nice to have it sticking proud just a little bit above the jaw height so that I can touch all 4 surfaces. Now that I've got my part fixtured, I'm going to want to turn my attention to the tool. Now there's a few different ways of holding the tool. The most simple way is to use a collet like one of these, but for this job I'm going to use a ER32 collet holder, which is going to operate similarly to the ER20 in the CNC router, but it has a R8 shank on the back, so they can be inserted and removed as needed. To install the collet, we're going to take the narrow cylindrical part and insert it into the spindle. To hold it in place, first we want to tighten the drawbar to take out all the slack, and then to tighten it the rest of the way, we're going to put a second wrench onto the spindle shaft here and tighten the drawbar against it. Now the first tool that we're almost always going to use is this tool here called an edge finder. And essentially what it does is it has a little part on the end that's not connected to the main spindle shaft and is free to wobble. And what we're going to do is, as we inch it closer and closer to the part, ultimately it's going to pull to the side just like that. And that's going to show that our little cylindrical section is in continuous contact with the edge of the part. Since that cylinder is exactly 0.2 inches in diameter, that means that we can set the y-axis now to be minus 0.01 inches. Another thing to note on this screen here is these edge finders do not like being run at high speed, and so here down at the bottom you can see where I've used the manual data input, or MDI, to manually set the machine to a low spindle speed, here 500 RPM, and turn it on. Now that the Y is set, I can set the X-axis the exact same way. I'll also configure the Z home using the sheet of paper trick that you've probably seen with the CNC router, just slowly stepping it down in Z by a small increment until it traps a sheet of paper between the tool and the part. All that's left is to load up the G-code using this button here. We can preview what it's going to do in the top right, paying especial attention to the crosshairs to make sure that where we currently are makes sense relative to what it's going to do. And then all we have to do is press cycle start. Now, while the machine is running, two things to keep an eye on are the feed rate and spindle speed override buttons here and here, which will allow you to, on the fly, change how aggressively the machine is moving. I often like to start these a little bit below 100% when I'm new to a tool or a material or just an overall strategy, and I can always crank it back up to 100% or even over 100% later on if I'm feeling comfortable. And so I'm going to leave you with footage of the machine running this part. Bear in mind this is played back at 2 times speed, just so we don't have to sit here and watch it too long. But you can see it starting off with that slow, gentle ramp down into the part to create that starting hole. Remember that end mills do not like to plunge, so doing this ramp really helps make the tool last a bit longer. And now as it gets towards the bottom of the hole, I'm just sort of going to reset up the camera here, and we're going to see it clearing out that pocket larger with this ever-increasing flattened circle shape. Now, I ought to be oiling the tool as it's running here. Aluminum is very sticky and it loves to stick to the cutter as it's going, but it's difficult to hold the camera and work all this stuff at the same time, so I'm being a little naughty here. But you definitely want to be careful. Aluminum can very easily gum up the tool and make a big mess. So definitely you don't need lots of oil, but a little bit all the time is a very wise maneuver. So please keep that in mind. It never hurts to have things lubricated, but especially with soft stuff like aluminum. It's a good idea. But that's it. Thank you very much for watching.